So Dalton was not completely correct when he stated that all atoms of a given element have the same mass, because different isotopes have slightly different masses. But that doesn't mean we throw out the theory, it just means we modify the theory. We can calculate an average mass. This is called the atomic mass for each element. So remember that atoms are really, really small, way too small to see. So anytime we're dealing with an amount of stuff that we could see, even with a microscope, we've got several bajillion atoms in there. And so then exactly how much each of them weighs doesn't matter. We're more interested in the average mass, right? Because we're dealing with a huge number of them. So if we look on the periodic table, directly under the element symbol, and here's the square for chlorine, so here's chlorine, Cl, and underneath is a number that's not a whole number. This is the average atomic mass of all the isotopes that compose that element. So there is no chlorine atom that weighs 35.45 atomic mass units. But if you take a bunch of them and look at the average mass, the average will be 35.45 atomic mass units. And these values are calculated based on the natural abundances of each isotope. So again, looking at chlorine, 75.77% is chlorine 35. Chlorine 35 atoms have a mass of 34.97 atomic mass units. The mass of the isotope is very close to the mass number, but it's never exactly the same. And again, that's something you'll learn about in Chem 1B. 24.23% of chlorine is chlorine 37. The mass of chlorine 37 is very close to 36.97 atomic mass units. So we can calculate the average. Now, when you're dealing with just a few objects, the way you do an average is you take the mass of each one, you add them up and get the total and divide by the number of objects, right? But if you're dealing with 5 gazillion atoms, it's going to take you more than your lifetime to add everything up, so that's not going to be practical. So we use a weighted average. We have the percent abundances. We know that 75.77% is this one. So we take the percentage and convert it to decimal form, dividing by 100. So it's a fraction now, 0.7577 out of 1. And we multiply by the mass of that one. We get a number. The other isotope is chlorine 37, 24.23%. We convert that to a decimal form, 0.2423, multiply by its mass. We get this value. You add those two masses together, and that gives you the average. You could use the percentages, multiply by the percentages, add them together, and divide by 100. But this method, we just do the dividing by 100 right away. So let's practice. Magnesium has 3 naturally occurring isotopes with masses of 23.99 AMU, 24.99 AMU, and 25.98 AMU, and natural abundances of 78.99%, 10%, and 11.01%, respectively. When it says respectively, and you've got a couple of lists, what that means is that the first one in the first list goes with the first one in the second list. They're given in the same order. It says calculate the atomic mass of magnesium. So we want to take the percent abundance, 78.99%, and express that in decimal form. So 0.7899. And I'm going to multiply by the mass of that isotope. So I've got the 78.99% with the 23.99. Then the next one is 10%, so that's 0.100, times its mass, 24.99, atomic mass units. So 10% goes with 24.99. And then I'm going to take the last one, 0.1101, 11% divided by 100, times its mass, 25.98 atomic mass units. So 11% goes with 25.98. And when you do a problem like this, you really should write this down. I know it's possible to do it without writing it down, but it's excellent to get some practice in writing stuff down, because we're going to get to some stuff that you can't just do on the calculator without writing things down. We also need to be able to write it down to show someone else how we did it, like showing your instructor how you did it, because there are many times where the assignment says show your work, and if you don't show your work in a way that I can figure out, I won't give you credit. It's just a thing that scientists have. The other thing is, especially on an exam, if you write it out like this on the scratch paper or the margin or wherever, you've got places to write stuff, then when you finish the exam and you want to go back and check your work, you have it all written out. You can look at it and see, did I copy down the right numbers? You can do the calculation on your calculator, and you can do it very quickly instead of having to start from scratch. So 0.7899, I messed up already, times 23.99 plus 0.1 times 24.99 plus 0.1101 times 25.98 equals. So my calculator is going to show me 24.309099. The unit would be atomic mass units. When you do a calculation like that, I would recommend always running it through your calculator twice. It's very easy to make a mistake. If you do it twice and you get the same answer, you're either really consistent in making mistakes or you did it correctly. If you get two different answers, do it a third time and go for best 2 out of 3. So did anybody else get that number? Okay. Because I screw up, and so I need you to be my second calculation. Should we record all these digits? Probably not, right? Here we have multiplication and adding, and so things can get a bit awkward. So we could go through the rules for sig figs and follow them exactly. I'm not going to require that of you for a problem like this. I think it's more important to use a reasonable number. All of these have 4 significant figures. The masses head 2 decimal places. So if I round this to 4 significant figures, I've got 2 decimal places, and that just kind of matches up with all of the other numbers. And so that's what I would recommend doing. Express this as 24.31 atomic mass units. Any questions? (24.31). How do they measure the mass of these different isotopes? They're too small to put on a balance, so how can you do that? Well, that was a puzzle, and that led to mass spectrometry. So this is an illustration of a mass spectrometer. This allows us to separate particles according to their masses. So what happens is you inject your sample, it gets vaporized by a heater so that whether it was solid, liquid, gas, it's a gas now. It comes through here, and there's an electron beam that ionizes the sample. So shoots an extra electron on it so it has a charge now. Then it goes through an electric field. So we have electrically charged plates here with slits in the middle to allow the particles to pass through. And the field here accelerates the particles. We need a charge on the particles because otherwise we can't control them. So we get a charge on them, and then we can use an electrical field to make them go faster. Then we shoot them through a magnetic field. And the magnetic field is going to bend this beam of ions, and the deflection, the amount of deflection, will depend on how heavy the particle is. The heaviest particles will get bent a little bit. The lightest particles will get bent the most. And so then on the detector here, this is an electrical detector. We get an electrical signal. We run it into a computer to identify what stuff is going on here. You can imagine the actual details of this instrument are quite complicated. The idea is pretty simple. We can separate them based on their masses and identify how many of each mass there are by the amount of signal that we get. So the position on the detector gives us the mass of the isotope. So this is what a mass spectrometer output might look like. And so we see that this mass 107 atomic mass units, this one got bent more than the 109. And then we can look at the intensity of the signal at each of those positions. And this one, there's always one that's given 100%. And then there's another one, the rest of them will all be less than 100%. You make the strongest one 100%. So the position tells us the mass, the intensity tells us the relative abundance. I think there is one homework question that asks you to do that, and so this tells you how you translate the intensity of the peaks into a relative abundance. So you take whatever the intensity is. So for 107, it's 100%. For 109, it's 92.9%. And you divide that by the sum of the intensities, and that will give you the relative percent abundance. The homework problem is a picture much like this, and you might ask, well, from this blue line, how do I get 92.20%? Well, you wouldn't. So on the homework, you'd look at this and you'd kind of eyeball it, and you might say, well, let's see, I think it's a little above 90, or maybe you think it's 90, and for the homework, that's close enough. Practically speaking, we've got a computer, and the computer is going to tell us exactly, or much more precisely, what the percent is.